Hi everyone. So it is a brand new day and I didn't get through everything I want to cover yesterday, so I'm breaking it up into another video. Today we are going to talk about another perspective on diffusion models, which is through the perspective of stochastic differential equations. Since this is a new video, let me just do a quick recap of the previous video. In the previous video, we have talked about how diffusion models basically map a probability distribution to another probability distribution. And we have discussed the forward diffusion process, right? The forward diffusion process is really summarized by this one-step equation, which is we multiply the previous state by some factor and we inject noise, right? It is a process in which we corrupt the real-world image. And the backward diffusion process is a process in which we try to reconstruct the original image. The key equation over here is that we can get the previous state through a linear combination of our current state and our prediction of the initial state x0 with some noise. And this prediction of the initial state is done by the following equation, which is basically just by making x0 the subject in the n-step forward diffusion equation, where we use a neural network to predict the cumulative noise from x0 to xt. This fully specifies the backward diffusion process, and we can calculate our objectives. Through all our work yesterday, we have managed to get that the objective really reduces to minimizing the sum of the mean squared error of the cumulative noise. Some constant Ct prime times the mean squared error of the actual cumulative noise minus the predicted cumulative noise. To train, the final conclusion that we have is, firstly, we should sample a time step t uniformly across the set 1 to t. Then we pick an image x0 in our data set. We run the forward diffusion process to get our latent variables, which are the intermediate states, x1 to xt. And we can run the backward diffusion process to get epsilon theta hat xtt. In our forward diffusion process, because we have calculated out the latent variables x1 to xt, we know the cumulative noise epsilon t at each time step. And so we can calculate our loss, right? Our loss for this will just be the mean square error of epsilon t minus epsilon theta xtt squared, and we just run backpropagation and do a gradient descent. And this is the training process for the diffusion model. And one thing we can note about our diffusion model is that it kind of resembles a Markov chain, right? So we have some states, we have transitions between states. So if we look at our diffusion model carefully, we will realize that it is a Markov chain. And in particular, it is a discrete time Markov chain, right? So after every time step, we will advance from one state into another. Even in Markov chain, there is this theory of continuous time Markov chain. So your time doesn't need to be a discrete value. And this is really going very close to the idea of a stochastic differential equation. For example, if we look at the forward diffusion process, right, we have xt is equal to some multiplier times the previous state plus some noise, right? So I will just use zt here as the noise that is injected at time t. So zt is this normal 0i random variable. So the question to ask over here is, what if we try to make this process a continuous one? Meaning we don't necessarily advance to a state in one time step, right? You see the transition here is from t minus 1 to t. What if we want to make this continuous? Well, in the continuous case, firstly, let's talk about this variance schedule beta t, right? Our beta t can no longer be indexed by natural numbers. This t must be a continuous one. So the idea is that beta t now describes a rate. It is the rate of decay of the signal, right? Because we are multiplying square root 1 minus beta t to the previous state. So if we look at this term carefully, square root 1 minus beta t, we know that beta t must be very close to 0. So remember the principle that we want the signal to degrade slowly across each infinitesimal time step. So if beta t is something infinitesimal, this square root 1 minus beta t will be, like by Taylor expansion, this will be 1 minus beta t over 2. And because we are thinking about it in infinitesimal time step, really this should be something like 1 minus beta t over 2 dt. And therefore, if we want to transform this equation over here to something that is in the stochastic differential form, xt plus dt is equal to square root 1 minus beta t. That will be 1 minus beta t over 2 dt times xt, right? Because we are considering a time difference of delta t. And I add the square root of beta t. As for the noise, we want to consider the incremental noise that's injected between time t to t plus dt. So I'm just going to label it as z delta t, right? And this should give me, if we bring the xt over to the other side, that would be precisely dxt is equal to minus beta t over 2 xt dt. And the infinitesimal noise that's injected, that's precisely dw, right? If w is the standard Brownian motion, then dw is precisely the noise that is injected at that time frame, correct? So it's going to be plus square root beta t dwt. And this is the stochastic differential equation form of the forward diffusion process. So let me just write over here SDE for the forward diffusion process. And let me just point out over here that this is really very nice, right? It is saying XT is a process in which we continuously degrade a very nice image into noise. DXT is how our image degrades per an infinitesimal time step. And this is really saying, well, at each infinitesimal time step, I'm going to drift towards the origin. I want to degrade this signal, so I'm going to scale it towards the origin. So this is a scaling towards the origin. The origin over here refers to the 0.00000. And then I'm going to inject some noise to it just to make it look more like a Gaussian distribution. So this is really the noise injection term. Wt is the Brownian motion, dwt is the noise that's injected at an infinitesimal time step. And these coefficients, meaning the beta t, just makes sure that they scale appropriately. Let me just point out over here that diagrammatically, right, if we just imagine ourselves in a 2D space, this is really saying, well, our current state can be somewhere here, right, as a vector in 2D, xt. dxt is the change in our current state after an infinitesimal time step. The first term is really saying I'm going to drift towards the origin, right? So the origin is here. Maybe the drift will land somewhere in this x point. And then the latter term is going to inject some noise to make myself look more like a Gaussian distribution. So that's kind of like diffusion. And you're going to end up somewhere around this point where you have drifted to. So that is the diagrammatic interpretation of this stochastic differential equation. Given that we have such a nice form for the forward diffusion process, I guess a natural question is, can we get a similar stochastic differential equation for the backward diffusion process? So the question is, can we get a similar stochastic differential equation for the backward diffusion process? Based on what we have derived in our previous video, we know that it is not so easy. And this is really the niceness of stochastic differential equation because so many mathematicians have worked on it. We actually have a great repertoire of results and we should just use them. So one way to get a stochastic differential equation for the backward diffusion process is to consider what the stochastic differential equation implies for the evolution of the probability distribution of our state across time. There's a lot of English, so let me just write it down in words. Our xt is now a stochastic process, right? It is a collection of random variables that's indexed by time, and each xt corresponds to a probability distribution, right? Because each of these xt is a random variable, they will correspond to a probability distribution that I will label as pt. So since xt is indexed by time, pt is also indexed by time. Because xt is a stochastic process, we should have an idea of how pt evolves across time. And if we can understand how pt evolves across time, we can get out how pt evolves if time was passing backwards. And from that, we can get the backwards stochastic differential equation. So that is going to be our goal. Let me just write out the plan over here. So from xt, we should be able to get how pt evolves across time, right? The probability distribution for each of the x. So once we have gotten pt, we will try to see how does ptt evolve backwards in time. And then we can get the stochastic differential equation for the backward process. So at least this is the plan. Now we have to execute it. We need to find out how to solve each of these three arrows. And let me just write it out. So the first arrow can be solved by what we know as the Fokker-Planck equation. Fokker-Planck equation can be viewed as a tool in which we convert a stochastic differential equation into the evolution of its probability distribution. The second arrow can be achieved through ordinary differential equation tricks. And the third arrow is again by Fokker-Planck equation. It seems like all three arrows are achievable, so we'll just proceed with it. The first arrow is really saying, given xt, a stochastic process, how do we get the evolution of their probability distribution across time? The answer is to use the Fokker-Planck equation. So what does the Fokker-Planck equation say? The Fokker-Planck equation is more general. It is saying if we have a stochastic differential process of the form dxt is equal to some general function of xt t dt plus some other general function gxt t dwt, then the probability distribution will change in the following way. I'll just write out the equation first and we can analyze it later. This is equal to the negative of the divergence of the probability density weighted by the drift plus the divergence of a diffusion tensor dot product with the gradient of the probability distribution. Okay, so now let's begin to analyze this. So what does this stochastic differential equation say? The change in the stochastic process xt is given by some drift. This f should really be seen as a drift term. You know, in the physics world, x, you can think of it as displacement. Then the f xt t dt, you should think about it as a velocity times time, right? So this velocity, precisely this f xt t term, is the drift over here. And this term gxt is the diffusion term, right? It is a coefficient that is multiplied to a random noise that's injected at this particular infinitesimal time step. And because of these two interpretations, when we write out our Fokker-Planck equation, the left-hand side of the Fokker-Planck equation is really saying, how does the probability density at the position and the time that I am at now change with respect to time? So a visualization I like to imagine is, let's say I am in a desert, right? There's a lot of sand around me. So you can think of the sand as like the probability density. If I'm standing on top of a sand dune, then that means I'm at a location with very high probability density. The amount of sand at any particular location at some given point in time is the probability density. And how does this probability density change with respect to time, right? You know, you can have wind that is blowing across the landscape. So the sand will fly everywhere. And that resembles how probability density is redistributed or evolving across time and space. So the left-hand side is really saying, how does the amount of sand at the point that I'm standing at the current point in time change with respect to time? So at any given instant, am I going to receive more sand from the wind and diffusion, or am I going to get less sand because sand has been blown away from underneath my feet? And the right-hand side is really using the terms in the definition of the stochastic differential equation that we have formulated. If we have a very high drift, so for example, if F is very high near me, that means the wind is very strong near me, and therefore sand is going to blow away quickly from my current location, right? So we should expect sand to be decreasing if F is very strong. But of course, like this F is just the wind, right? If you have no sand underneath your feet, it doesn't really matter if the wind is strong. Like no sand is going to escape you because you have no sand underneath your feet. So what we really care about is the amount of sand beneath us weighted by the wind. So this is precisely this P times F term. P is the probability density and it is weighted by the drift. And we take the divergence of it. So in vector calculus, the name divergence is very aptly named because it is really a measure of how much things are going out from your current point. If things are in total going out from your current point, then divergence should be positive, otherwise it is negative. And over here, if the drift weighted by the amount of sand near you has a positive divergence, it means that sand is just in net effect escaping from your region. And therefore, if the divergence is positive, the probability density should be decreasing. And that's why there's a negative sign over here. right? So I guess to summarize, this is really the divergence of the drift weighted by the probability density. This second term relates to the diffusion term over here. How does diffusion affect the amount of probability density or the amount of sand that I'm receiving at my current point? Well, I need to have a sense of measure how much I am diffusing relative to my neighborhood. If all the points in my neighborhood are diffusing with much more, I guess, power than me, then I'm going to receive a net influx of sand or probability density. But if all the points in my neighborhood are diffusing with less power than me, that means I am diffusing with a larger power. In effect, sand should be escaping from me. And this is where this combination of divergence with the gradient comes in. So we know that the divergence of the gradient is the Laplacian. And the Laplacian is really a measure of a function evaluated at your current point relative to the function evaluated around your neighborhood, right? It compares you versus your neighborhood. And in general, if the function evaluated at your neighborhood is larger than you on average, then the Laplacian is positive. Otherwise, it is negative. This should make a lot of sense. If the Laplacian of the diffusion term is positive, then it means that your neighborhood are diffusing with a larger power than you. So you should get a net influx of sand. That's precisely why the sign over here is a plus term. So I'm just going to write here that you can regard this as the Laplacian of the diffusion coefficient. Since we have discussed the Fokker-Planck equation, we should just apply it to our current context. So in our current context, the stochastic differential equation is dxt is equal to, let me try to remember, minus beta t over 2 xt dt plus square root beta t dwt. In particular, our fxt is equal to minus beta t over 2x. And our gxt is equal to square root beta t. It is not even dependent on x, right? And therefore, we can write out the probability density ODE for forward diffusion process as, just by using the Fokker-Planck equation formula, partial pxt partial t is equal to minus the divergence of p times f, and our f here is minus beta t over 2x plus, so the second diffusion term, g is square root beta t, gg transpose will just be beta t over 2, and we can bring that constant out, so it will just be the divergence of the gradient of p, which is the Laplacian. It's just beta t over 2 times the Laplacian of p. This is an important equation, so let me just box it up. We now know how the probability density evolves in the forward diffusion process. So just to simplify the equation a bit, I'm going to bring out the beta t over 2 and apply the divergence to just px, because this divergence is with respect to space. It is not with respect to time. Plus beta t over 2 Laplacian of p. So we have accomplished the first arrow. So for the second arrow, we need to know how to run this PDE, now a partial differential equation, backwards in time. And this is pretty straightforward. In the stochastic equation, we can't easily run it backwards in time. And that is really because at every time step, we are injecting some random noise. How do you reverse the injection of random noise? That is something that is unclear in the stochastic differential equations world. But in the PDE world, it is very clear how to run things backward in time, right? So to run this PDE backwards in time, we just need to negate the time derivative operator. So in particular, if we define tau to be t minus t, then d tau is just equal to minus dt, right? So over here, just to not confuse us, I'm still going to use the variable t instead of tau, but we should just realize that all it takes is just to negate the coefficient of any derivative with respect to the original time t. So the backward PDE for probability density is partial pxt partial t equal to minus beta t over 2, the divergence of px minus beta t over 2, the Laplacian with respect to t. Because the only place where the partial of t happens is at the denominator over here. So all we need to do is just to flip the sign of all the terms on the right. With this, we have accomplished the second arrow. Almost. There is one slight problem because the ultimate goal for us to even write out this probability density PDE is we want to convert it back to a stochastic differential equation. Let's just recall the Fokker-Planck equation. In the Fokker-Planck equation, we have the general form dxt is equal to fxt t dt plus gxt t dwt. And this corresponds to the probability density PDE, which is partial pxt dt is equal to minus the divergence of pf plus the divergence of the diffusion tensor dot product with the gradient of p. So the constraint over here is that if we look at this second term, half GG transpose should be something that is a positive definite. If we look at this term minus beta t over 2, the sign is wrong, which means that we cannot convert it back to the stochastic differential equations form easily. Fokker-Planck equation only tells us how to convert between these two if the coefficient in the diffusion term of the probability distribution PDE is something that is positive definite. But as with all things, there is a trick to this, which is if we look at the probability density in the backward PDE carefully, right, this Laplacian term, we know that the definition of Laplacian is the divergence of the gradient. And this divergence over here is very similar to the first term, which means if we can somehow absorb things into the first term to make the second term positive definite, then it will be very good for us and we can convert this backward PDE into the backward stochastic differential equation. However, there is another constraint, which is that the first term requires multiplier of p for us to get a reasonable form of f. So we have to massage this term some more, right? And there is no problem actually. So the divergence of the gradient of p is the divergence of, so the gradient of p is really equal to p times the gradient of log p. And I hope it makes sense why massaging the Laplacian of p in this form really helps us to convert the backward PDE into something that is easily convertible to a backward stochastic differential equation, right? If we look at the backward PDE again, partial pxt partial t is equal to, let me just copy out the equation, right? This is equal to minus beta t over 2. The first term stays the same. As for the second term, we really want to convert it into something that is a positive coefficient times the Laplacian of p. If we look at our forward PDE, this is our forward PDE, or how the probability distribution of the forward diffusion process evolves, we see that the latter term is a positive beta t over 2 times the Laplacian of p. And it will be ideal if the backward process has something of a similar form. So I'm just going to do some wishful thinking and I'm going to write plus beta t over 2 times the Laplacian of p. And because I added this term, I need to subtract beta t times the Laplacian of p to make these two things equal. Because we have done the massaging of Laplacian of p, this equation becomes minus beta t, the divergence of p, the gradient of log p. And we can bring these two terms into one. These two terms become minus the divergence of p times beta t over 2x, right? We bring this coefficient inside, and over here, we bring the beta t inside to get plus beta t, the gradient of log p, plus the diffusion term. And this is very nice because this is precisely in the form of Fokker-Planck equation, right? We can define this as our f prime and this as our g prime. And this implies out the backward stochastic differential equation as dxt. So let me write tilde to denote the backward diffusion process. So dxt tilde is equal to, the f here is this entire term, right? So this is equal to beta t over 2 xt plus beta t, the gradient of log p times dt plus square root beta t dwt, right? So note that this term beta t over 2 is actually half g transpose. In particular, this g is the same as in our forward diffusion equation because we made it so it is a square root beta t dwt. I also just want to note here that this Wt is a different stochastic process than what we use to simulate the forward diffusion process. So I'm going to write it as Wt tilde. That's very nice. We got the backward SDE. So over here, right, between these two steps, all we wanted to do is to make the term that corresponds to the diffusion coefficient something that is positive. And to do that, we just made this design choice that it would be nice if the diffusion coefficient for the forward process and the backward process are the same at square root beta t. Note that we could have added any constant times the Laplacian of p as long as it makes the coefficient positive, definite. And we can just subtract that corresponding constant, and that will give us a whole family of backward stochastic differential equation that corresponds to our backward diffusion process. We made this design choice that gets us this unique backward stochastic differential equation. Another thing that we can do over here is we can analyze our backward stochastic differential equation. So this first term, this is precisely the same as the drift term in our forward stochastic differential equation, right? So our forward stochastic differential equation, just to recall, is dxt is equal to minus beta t over 2 xt dt plus square root beta t dwt, right? This term, beta t over 2 xt, is precisely the counteracting drift of the forward diffusion process. So that makes sense. And we have this additional term over here. And this is really in physics what we call as the forcing term, right? Basically, in the forward stochastic differential equation, we have this diffusion term that injects noise. If we want to get the backward simulation of the forward process, we need to somehow reconstruct what is the signal given a noisier signal. And this requires us to know some information about the probability distribution. And it turns out that the information about the probability distribution that we need is just this term, so the gradient of the log probability. And this has a special name in, I guess, statistics. Well, it is not exactly the same definition, right? So this gradient is with respect to space, and this is what we call as the score. The score is the gradient of the log probability. So in statistics, I just want to make a note over here. So in statistics, the score is also the gradient of the log probability, but this gradient is with respect to the model parameters theta. In diffusion models literature, the score refers to the derivative with respect to space instead. But again, I think it is a similar idea. It is really saying at a particular point in time and in space, where is the direction that you should go to maximize the log probability? And this must be the forcing term or the additional information that you will need to retrace what the forward diffusion process does. The forward diffusion process is just an injection of noise. And if you want to go backward, you need to have some additional information about the probability density, and the score is all you need in this case. And the last term is the diffusion process. This is very interesting because we have a forcing term and we also have a diffusion term. And based on what I've said just now, it is really a design choice as to what we choose to be the coefficient of this diffusion term. We made the design choice to choose it as the same coefficient as the forward diffusion process, square root beta t. But it could actually be of a much larger magnitude or be of a smaller magnitude as long as it is positive definite. And we notice that if we make this change, the forcing term will also change. The coefficient of this diffusion term and the forcing term correlates with each other. If we want to increase the diffusion term, we will need to increase the coefficient of the forcing term as well. So there's really this nice balance of diffusion and the forcing term. And this all comes back to the physics intuition of diffusion models. So to make sure we remember that point, I'm just going to note over here that different combinations of forcing term and diffusion term work as well for the backward diffusion process's stochastic differential equation. As we have seen so far, the backward diffusion process is one of the harder things to get results of, right? So this backward stochastic differential equation, we should try to understand what we can do with it in the machine learning context. So the backward stochastic differential equation, just to copy out the equation from earlier, is this stochastic differential equation is trying to tell us, well, if we start out from the end of our diffusion model, which is the xt, we can really just simulate all the previous states if we know the score. This is the score, the gradient of the log probability. If we know the gradient of the log probability, we can just simulate the backward diffusion process immediately. But the problem is we don't know this score, right? P, the probability density, is exactly the thing that we're trying to find. So we don't know the score. But this stochastic differential equation is telling us that the score is all we need to know. So why not just use a neural network to predict the score? So I guess just to make it clearer, I'm going to use S as the symbol for the score. S is a function of the displacement and the time. dt plus square root beta t dwt, where sxt is the score, which is the gradient of the log probability at xt. And so the conclusion is, why not just use a neural network to predict the score? And that is exactly what we are going to do. So let me just formalize it in mathematical symbols. So what we are trying to do is we will train a neural network model S theta. S theta will take in two arguments, xt and t, and it will give us some estimator of the actual score, right? So S theta is something that takes in R32 by 32. So in our problem setup, it is the 32 by 32 pixel image times t. T is now continuous, so it's definitely in R. Or if we want to embed it, it can be in RD for some dimension. And it will give us the score. The score is the gradient of the log probability, so that is still in R32 by 32. Then the question is, how do we train this neural network model? Because to train such a model, we would need to know the true score. But as I've said earlier, we don't actually know the true score. So we have to come up with some clever idea about how do we get an estimator for the true score to do our stochastic gradient descent on. So our goal is to find an objective such that S theta learns the true score. So again, when we want to tackle this, we should try to understand what the true score is actually doing, right? So the score is the gradient of log p. And if we want to score at time, say t, with a position of xt, we can do the following. First, we know how to take the derivative of the log. This is equal to the gradient of p of xtt divided by p of xtt. Then we try to fall back to some of the ideas we had from earlier, which is it will be very nice if we know the starting point, right? Because the forward diffusion process is very easy to understand. So why not just condition on the initial state? So if we condition on the initial state x0, conditional probability will give us the gradient of the integral over the space of x, which is R32 by 32, p, for the sake of clarity, I'm going to absorb the t argument of p into the subscript. And I'm going to write it as pt xt given x0 times p0 x0 dx. This is really saying to get the probability of me being in state xt at time t, I'm going to condition on all possible initial states, and I'm going to multiply that by the conditional probability, and I'll integrate over all the possible initial states. The denominator can just remain as it is. I'll just write it in a similar form and use t in the subscript. And since the whole point is to find a tractable objective for this real score, what we really want to do is we want to write out this whole thing in terms of an integral or an expectation in which we can do stochastic gradient descent on. And because the only thing we can actually sample is over x0, which is the point in our data set, we want the integral or the expectation to be something that is over x0. The way that we want to do that is we want to convert things in terms of x0 given xt. To achieve that, we are really trying to see if we can find some place to use Bayes' rule in this formula. Really resembles the Bayes form, right? And we want to apply the Bayes rule, but there is this derivative over here, so we have to settle that somehow. If we take the derivative inside, well, it will not worry about this p0 x0, but it will do the gradient on pt xt given x0, and that will disrupt the Bayes form. But we notice we can apply the mathematical trick earlier, right? Which is we can write out the derivative of pt xt given x0 as the probability itself multiplied by the gradient of the log probability. So this is equal to the integral over R32 by 32 pt xt given x0 p0 x0 times the gradient of the log probability pt xt given x0. Of course, the x0 over ptxt. Now, these three terms can really be combined into the Bayes form. And we should be able to get the integral over R32 by 32 P0 x0 given xt, the gradient of ptxt given x0 dx0. And this integral is over x0. We have our probability density over here. So this is precisely equal to the expectation of x0 sampled from the probability density at time 0 conditioned on seeing the state at xt, the expectation of the score at time t, which is the gradient of log pt xt given x0. We have done a lot of mathematics over here, but now it actually makes sense to use English to say what we have achieved. We have established that the true score at time t is equal to the posterior expectation, right? This is over a posterior distribution. Posterior meaning after you have seen what you can currently see, which is the current state xt, the updated distribution of x0. So the true score is equal to the expectation of the conditional score. So let me just write it down. The true score at time t is the posterior expectation of the conditional score at time t. So just to piece it out together, so the true score at time t is equal to the spatial derivative of the log probability density at time t. It is equal to the posterior expectation. So the posterior expectation is over x0, and it is an updated distribution on x0 given that we have seen xt, right? So this is really the what is underneath the expectation, which is x0 sampled from the posterior distribution of the conditional score. So the conditional score at time t over here really refers to this spatial derivative of log ptxt given x0. Right, it is the conditional score because we are conditioning on the initial state x0. Just want to mention over here that this is precisely another motivation for estimating x0, right? You remember in our previous video, we estimated x0 by x0 hat. And this is really why we are so obsessed about x0, because it is something that we can sample from, and with it we can enable a lot of capabilities from this stochastic differential equations perspective. So now unfortunately we actually have two new problems which I'll denote as I and II, right? So the first problem is, how do we sample from the posterior distribution? In particular, how do we perform this step? How do we sample x0 from probability density condition on xt? The second question is, how do we calculate the derivative of log ptxt given x0, right? How do we calculate this conditional score? Let me just give the answer. So actually, problem one is a problem that we don't need to solve, which is very nice. And we'll see this later on. So don't need to solve. The second problem, how do we calculate the conditional score? This is just mathematics. So I guess we'll just calculate it because there's actually something very interesting going on. So what is the conditional score? The conditional score is the gradient of the log of the conditional probability, right? So it suffices to just calculate what the log of the conditional probability is, and then we just need to take the gradient. So the log of the conditional probability, well, this is going to be very straightforward because we understand the forward diffusion process really well, right? Each of these xt is just some multiplier multiplied by the previous state plus some noise. And therefore, this is equal to, you remember from the n-step forward diffusion process equation, that is going to be xt is equal to square root alpha t bar x0 plus square root 1 minus alpha t bar some random noise. And so the conditional probability of xt given x0 is going to be a Gaussian, right? And if we take the log of the Gaussian, we will end up with some constant, let's say c prime prime. That's going to be log of the normalizing coefficient of the Gaussian distribution minus 1 over 2 times the square of the variance, right? The square of the variance is going to be 1 minus alpha t bar, right? It's just a coefficient in front of this injected noise squared. And the determinant is the identity, so that's equal to 1. then multiplied by the realized value. The realized value is xt minus the mean squared. So the mean is going to be this square root alpha t x0 term, and then we just square it. And for our purposes, we don't really care about this constant, right? Because we're going to take the gradient with respect to x anyway, so this constant effectively disappears. We're able to get that the gradient of this is equal to, the coefficient will stay as it is. The gradient of x transpose x is just 2x, right? So the 2 cancels out with the half over there, and we'll get 1 over 1 minus alpha t bar times the vector itself, xt minus square root alpha t x0. And because xt is equal to square root alpha t bar x0 plus some random noise, this term is just precisely the random noise, right? It's just precisely this random noise. So it is equal to epsilon t over square root 1 minus alpha t bar. And I think the upshot over here is that the conditional score is proportional to the noise, epsilon t. They just differ by a constant. So over here, we have sufficient information to actually train our models. In literature, this is called a score matching model because we are literally training a neural network to predict the score so that we can run the backward diffusion process. So to train a score matching model, we just need to formulate the laws as, so you remember we are doing all this hard work because we want some objective that we can do backpropagation on. The loss will be equal to the expectation. Firstly, we should sample t, right, uniformly from the interval 0 to t. So it is no longer going to be just a set of natural numbers, right? It's going to be an interval. And then we can pick a x0 from our data set, and then we find xt just from our forward diffusion process, right? So xt from p t xt given our data point. And what is going to be inside this expectation? Well, we are doing a score matching model. So the simplest idea is just to use a mean square error, which is we take the true score minus away our predicted score and we square the error. By definition of the true score is going to be the gradient of the log probability density at time t minus whatever our neural network predicts. And we want to use all the result of our hard work earlier, right? So I'm just going to copy the subscripts of the expectation for completeness. This is equal to, we don't know the true score, but we have expressed it in the form of a posterior expectation over the conditional score, which is something that is easier to compute. So this is going to be the posterior expectation of the conditional score minus our prediction of the actual score squared. And this is equal to, well, since we have calculated what is inside the expectation, let us just use the result. The expectation of x0 over the posterior distribution of, yeah, so sorry, I forgot a minus over here, but this is going to be the posterior expectation of minus epsilon t over square root 1 minus alpha t bar minus s theta xt squared. So you see that our neural network model to predict the score is really just predicting the cumulative noise that is scaled by the variance schedule. That is almost equivalent to the neural network model that we have trained in our previous video. So this really goes to show the stochastic differential equations perspective on diffusion model is really the equivalent to that of the Markov chain perspective. Ultimately, the neural networks are all predicting this cumulative noise because it is equivalent to predicting the true score in some sense. They are just off by a factor. And I think in most of the training pipelines, they don't use this square root 1 minus alpha t bar anyways. Essentially, we are training the same model which predicts the cumulative noise, which is some scaled version of the true score. So this is also some motivation why we predict the cumulative noise in our previous video as well. So I just want to hammer in one more thing, which is we haven't really talked about our problem number 1, right? Which is how do we actually sample x0 from this posterior distribution? Well, it turns out that we don't need to because of this well-known fact in statistics. If we have a predictor, let's say y hat for some true value y, which is our target in this prediction, can be something that is noisy. it can have some inherent noise that is just not predictable. So the best that we can do in such a scenario is to predict the expectation of y. So usually people can decompose this MSE into the form of, you just subtract off the expectation of y, you add back the expectation of y, and you consider these two terms separately, because there is no way we can do better than just to predict the expectation of y if y itself has some inherent, let's say, observation noise. And this is equal to, because these two vectors are orthogonal in the Hilbert space, we can write it as y minus the expectation of y squared plus the expected value of y minus y hat squared. And this is going to be equal to the variance of y, or the sum of the variance of the coordinates of y, plus the expected value of y minus y hat squared. So why am I saying this? If we look at the objective, it is really in the form of the expectation of the conditional score minus our prediction of it squared. This is in particular equal to the norm of just the conditional score minus our prediction squared. Sorry, I forgot the square here. Minus the variance of y. But the variance of y is something that is constant, and in our laws, we don't really care about constants, right? When we do our backward propagation, we only care about the gradient of the loss with respect to the parameters. And the constant is not going to depend on the parameters themselves. I'm just going to write that this is equivalent to just ignoring the expectation in the middle. By this mathematical identity, we have shown that if we just take out the expectation, the loss or the objective is going to change by just a constant that is independent of our parameters. So this is just equivalent to, let me just write out all the conditions again. Sample t, then sample x naught, then sample xt, the norm of minus epsilon t over 1 minus alpha t bar minus our prediction squared. So we can just calculate the conditional score, and we use that as a proxy for the true objective that we want and backward propagate with that. In theory land, this would work for training. So I guess just to summarize, firstly, s theta xtt is just predicting a scaled version of epsilon t. So this shows that epsilon t, the cumulative noise, and the score, the gradient of the log probability density, are equivalent in some sense, up to a scaling factor. And the second point that we can get from this is that using conditional score, so recall that this conditional score is really the derivative of the log probability of xt conditioned on the initial state x0 in the objective results in the same training process. And I think these are the two important things to take away from this stochastic differential equations perspective on diffusion models. In our first video, we really viewed things as just a Markov chain. And we worked out a lot of algebra, linear recurrence, right, multivariate Gaussian, and we obtained a set of forward diffusion equation and backward diffusion equation. But this stochastic differential equation perspective really puts things into place where we understand that in the backward diffusion process, there's really this forcing term, which is just the score. In other words, there is a drift that points towards points of higher log probability densities. And using this perspective, we can construct another objective based on just matching the score using mean square error, and it results in the same training objective as what we would have done if we followed the Markov chain approach, which is the mean square error on the cumulative noise. I guess the additional insight we got from this is that using the mean square error on the cumulative noise is equivalent to predicting the score, which in my opinion makes more mathematical sense because it is really saying we want to understand the direction and the magnitude that we should go in order to reach points of a higher log probability density. There is one more nice thing to using stochastic differential equation to look at diffusion models, and I will just mention this, and that will be the end of the diffusion model series. So the other nice things is what we would call the conditional diffusion models. For conditional diffusion models, so here is the problem setup. So in the image generation problem, we just want to generate an image that resembles something that we might see in real life. But if you think about how you generate image, you don't want to just randomly generate an image, right? The problem is we don't just want randomly generated image, right? We want to provide some label or text y. So this y can be like panda riding a bicycle and expect to receive that image. Basically, an image that is conditional on y. So let me just make it more visual. So panda riding bicycle is the y here, and we pass it to the model. We expect the model to really generate out an image that is like, a panda, a panda riding some sort of bicycle, right? It turns out that with the stochastic differential equation version of diffusion models, we can get it out for free. So recall the backward stochastic differential equations. That's going to be dxt tilde is equal to beta t over 2xt plus the forcing term, which is beta t times the score dt plus beta t over 2 dwt, right? That's the diffusion term. Again, we fall back to our physical understanding of this equation, right? This term over here is really a forcing term. If you think about forces in physics, this is really saying go in the direction of higher log probability density. And like in application purposes, it seems like we can just impute this term, right? Like if we want to force the model to generate some specific outcome, we can just change this forcing term in the direction where we want to go. So it seems like we can impute this. Right, the other terms of the stochastic differential equation are pretty straightforward, but this forcing term seems to be something that we can adjust a bit depending on our use case to generate the particular image that we want. So let me just rewrite it so that I can demonstrate what I mean by impute, right? So dxt is equal to beta t over 2xt plus beta t. If we want to generate images condition on y, we just need to consider the probability distribution of the images condition on y. And why not just use that score as the forcing term, right? It would be nice if we can have beta t times the score of a conditional distribution. So ptxt given y, right? We condition on y, what is the updated probability density? And we want to go in the direction of maximum likelihood. dt plus beta t over 2 dwt tilde, right? So we have imputed this as the conditional probability. Forcing term now points towards points with higher conditional probability. Visually, the distribution of real-world images is like this. Maybe pandas are here. So after you condition on y, where y is something like panda riding a bicycle, then we should expect the conditional distribution to be something like this, for example. And the score will be more likely to be pointing in the direction of pandas. And the noise term over here is used to ensure that we have some diversity, right? We don't want to get stuck at some local maxima. If we get stuck in a local maxima, ideally the noise that we have injected will bring us out so that we can continue to go in the direction of pandas. So, but, right, there's always a problem. So in this case, the problem is how do we get PT xt given y, right? This seems like a pretty hard problem because for every label y, we have to get an updated probability distribution. That is like solving the diffusion model problem capital Y number of times, where y is the number of distinct labels that you have. And that's just not feasible. In fact, we would rather solve the inverse problem, which is given x, what's the probability that it is talking about y, right? Given a picture, can you tell me if there is a panda inside? I think that's just a much easier problem to solve. We want to do this flip, and what other tool to use than just Bayes' rule, right? So to get the derivative of the log of ptxt given y, the conditional probability distribution, this is equal to the derivative of log. We just apply Bayes' rule over here, so we'll get pty given xt, ptxt, the marginal distribution of xt over p of y. We don't really care about the p of y in the denominator because if we perform this logarithm, the derivative of log of py doesn't even depend on x. right? So it doesn't really matter. So this is going to be equal to the derivative of log of pt y given xt plus the derivative of log of pt xt minus the derivative of log py. And we don't want to care about this, right? Because the derivative is with respect to x. And over here, this is actually very nice, right? Like we can analyze the other two terms. This is just the unconditional score. We know how to do this. Like this is in fact just our objective earlier, right? We are already trying to predict the unconditional score. So there should be no difference to what we are doing over here. This is the score of some classifier. So let me just write, by classifier, I mean it in the machine learning context where given an image, we try to predict what label or what bucket it should fall under. So given an image, like does it have a panda or not? That's a 0-1 question. So this is what we call as the classifier gradient or the classifier score. And so the idea over here is to train a classifier. So our classifier can just be another neural network model, right? I'm just going to denote it as Q phi, where like the phi refers to the parameters of the neural network model of y given x. This should return out a probability density that we can take the derivative of and use this classifier to guide the diffusion process so this is via the SDE perspective, right? So our target, right, is now this conditional score. So it is the derivative of the log of pxt given y. So our prediction is going to be based on xt, t, and y. And based on what we have obtained above, it is equal to the conditional score, basically the neural network that we have before, which is s theta xt t, the unconditional score, plus the classifier gradient, which is the derivative of log of q phi y given x. And in practice, we will insert a tunable parameter gamma over here. So this gamma really symbolizes the trade-off between sample qualities and diversity. Just to understand this, if gamma is equal to 0, our prediction model will just become the unconditional score prediction, and there is no awareness of y. So we shouldn't expect the images produced to even have any pandas in the first place. So that is where like diversity is maximized, because it is possible for us to get all sort of images, but we are not going to get any sample quality because we are not producing images with pandas inside. On the other hand, if gamma is equal to 1, in theory it is going to be predicting the conditional score. But we can also just boost gamma to be much larger than 1, and it should be increasing the sample quality, meaning we will be producing more images with pandas and bicycles inside. So this is at the cost of diversity, because by increasing gamma, we are actually imposing some constraint on the noise. We may be getting pandas riding bicycles, but maybe all of the same art style. So this gamma is really a parameter that dictates the trade-off between sample qualities and diversity. And I also just want to say that we should recall that there is some equivalence between score and the cumulative noise, right? The score is just the cumulative noise multiplied by some constant. And the equation is actually this. So S theta is minus the cumulative noise over 1 minus alpha t bar. If we are trying to do this from the previous video, our neural network model just needs to also take into account y. Because of this relation between S and epsilon, we will use the previous unconditional cumulative noise prediction, and we will subtract gamma over 1 over 1 minus alpha t bar of the classifier gradient. This is just to make sure we account for the scaling between S theta and epsilon theta. So this is just to show how we would update both objectives, one obtained from the Markov chain perspective and one from the stochastic differential equation. Now I just want to point out a disadvantage of this methodology, which is we have to train another neural network, which is the classifier Q phi. Generally, this is a problem because we have to consider how the neural networks interact. If we increase the performance on one, does it necessarily improve the performance on the other or the end-to-end task? That is really an unknown. And I generally feel it is very cumbersome to tie the training of neural networks together. So another idea is to use classifier free guidance. So this adjective classifier free is really saying, can we achieve the same thing? So can we guide points towards higher conditional probability density without training a separate classifier? And the answer is, of course, yes, right? Because people have achieved it. This is just a short follow-on from the previous classifier-guided equations. Let us look at our prediction above, right? So in the classifier-guided realm, we have our prediction, which now takes in y as an input to be the unconditional score prediction plus gamma times the classifier gradient. This is in the classifier realm, right? So if we take a step back, if we don't use the classifier, we are trying to predict the unconditional score plus gamma times the true classifier gradient. So the true classifier gradient, I can write it as the gradient of log of py given xt. But this true classifier gradient, pt y given x, by base rule is pt x given y, py over ptxt. If we combine the terms together, we can get gamma, the gradient of the log of this whole term will be the gradient of log of ptxt given y. Hey, this is the conditional score prediction again. We don't care about this second term, py, because that vanishes after taking the gradient. And we subtract the gradient of log of ptxt. And this is the unconditional score. All of these are true values. We don't actually know them yet. If we want to cast everything to prediction, so cast to prediction, we get the unconditional score prediction plus gamma times the conditional score prediction minus the unconditional score prediction, which is really equal to a convex combination of the unconditional score prediction and the conditional score prediction. And I think the key idea here is, why not just achieve both the unconditional score prediction and the conditional score prediction in one neural network? We just design a special token, phi. So this phi is now not a neural network parameter, right? This phi is just a special token to indicate that we are doing unconditional score prediction. The neural network we are training now, S theta, it now takes in our R32 by 32 image, which is our xt, followed by a time parameter, which is t, and a label or the null token in RD, which is y or phi. And it will map it to the score or the unconditional score prediction depending on this y, right? So which lives in space R32 by 32. And what this S theta does is, algorithmically, S theta xt t phi will just be the unconditional score prediction, S theta xt t. Otherwise, it will be the conditional score prediction. And we know how to do both. So the upshot over here is we train a neural network model that predicts conditional and unconditional score. And in the objective, we use 1 minus gamma s theta xt t plus gamma s theta xt t y to do the backpropagation. We use a convex combination of the unconditional score prediction and the conditional score prediction as the final prediction to calculate the error against the true value and to do backpropagation on. This allows us to just use one neural network model for the conditional diffusion model setup. And finally, we are done. I really did not expect to finish this, but I just want to quickly summarize what we have discussed across both videos. Because if you actually follow along and you have seen the things that I've talked about, there's really a lot of interesting ideas in diffusion models. And I think connecting all these concepts is a really difficult task. And I probably have missed out a lot of other crucial insights as well, which I would probably discover some other time in my life. For now, right, I think the summary is that in our first video, we went through the diffusion process. And in this, we learned the forward diffusion process and the backward diffusion process. We looked at the diffusion process in terms of Markov chain. where we start off with a sample in one distribution and we produce a sample in another distribution and vice versa. So the forward diffusion process is very straightforward, right? At each time step, we're really just applying a factor on top of the previous state and we inject some noise. The backward diffusion process is slightly more complicated because we need to reconstruct the signal from the noise. And the key thing to note here is that conditional on our current state and the initial state, we can express our previous state as a linear combination of the current state and the initial state with some noise. Then we talked about the objective for our diffusion process, right? The objective is how do we calculate our loss to train on. And in this Markov chain perspective, what we want the objective to be is to be the maximum likelihood or to maximize the log probability of seeing the data in our data set. But this is not feasible because of latent variables. So we met this latent variable problem. All the intermediate states in our diffusion process are latent variables. And so we resorted to a classical idea in variational inference, which is we use the evidence lower bound, which is the ELBO, as the objective, and we want to maximize this evidence lower bound. This resulted in a rather simple diffusion objective, which is to minimize the MSE of our prediction of the cumulative noise at every time step. We want to minimize the error of our prediction of the cumulative noise at every time step. Then today we went through the stochastic differential equation perspective of diffusion models. This is really a natural extension from the Markov chain perspective because the Markov chain perspective is really saying at every time step you proceed on to the next state or the previous state. So the time step is kind of discrete, but in stochastic differential equations, we just view time as a continuous variable. The insight that we got from it is that in the backward diffusion process, there is a forcing term that is proportional to the score or the gradient of the log probability density. And we need that term because we want to reconstruct the signal from the noise. So we need some information about where are the points with higher probability density. This is really the score. So it's the score at time t of xt. And the other insight that we have seen is that there is this equivalence of stxt with epsilon t. We see that they differ by only a constant that is dependent on the variance schedule. Now it makes sense why the objectives from both perspectives really converged. And we have also shown that the objective can be, right, this is a design choice, the MSE of score prediction, which is st xt minus st theta xtt. And we really see how these two objectives have converged, right? So on one hand, in the stochastic differential equations world, we chose to apply MSE on the score prediction arbitrarily, and we got that we should minimize the MSE of the score. On the other hand, in the Markov chain world, we want to maximize the log likelihood, but we can't do that, so we maximize the evidence lower bound instead. And it turns out that maximizing the evidence lower bound turned into minimizing the MSE of the cumulative error terms. And these two objectives are really equivalent because they differ by only a constant, which depends on the variance schedule. So in both cases, we made some design choice, right? In one case, we used the MSE arbitrarily. In the other case, we chose to use evidence lower bound because the maximum likelihood is just too intractable. And finally, because of this stochastic differential equations perspective, we are able to take a look at conditional diffusion models, where we solve a much more interesting task, which is instead of just generating an image randomly, we want to generate an image based on user input. And we see that with the stochastic differential equation setup, it just becomes the imputing of the forcing term in the stochastic differential equations. With that, we can have two methods. One is using a classifier gradient, and one is using a classifier-free way of imputing that particular term. Yeah, so thank you for listening through all of this. I think it is great to crystallize all of my thinking about diffusion models in this set of two videos so that in the future, if I need to review diffusion models, I don't have to walk through all these details again. And I hope that it is helpful. Okay, see you next time.